I was just saying that I'm beginning to recognize some of you people. I would ideally like to have a class with maybe just 10 students so that we can have a lot of dialogue and I can find out what you're thinking about, address your questions. That'll make a lot of fun, but that's not possible in an introductory course. But I think you should feel free to interrupt or ask questions or discuss any reasonably related issue that I didn't get to. Okay, that'll make it interesting for everybody, because I told you many times the subject is not new to me. It's new to you. So what makes it interesting for me is the fact that it's a different class with a different set of people with different questions. And trust me, your ability to surprise me is limitless, because even on a subject which I thought is firmly fixed in my mind, somehow you guys come up with some point of view or some question that always of interest to me or to people who've been practicing this business for a long time. So I welcome that, and that'll make it more lively. All right, so I think last time I got off on a rant about all the different pedagogical techniques, some of which I don't endorse fully. I'm going to go back now 300 years in time to one of the greatest laws that we have, because look at the power of this law, right? Here is the equation, and all the mechanical phenomena that we see around the world can be understood with this law. And I was starting to give you examples on how to put this law to work, because I think I at least made you realize that simply writing down the law does not give you a good feeling for how you actually use it. So maybe you have understood it, but I'm going to remind you one more time on how you're supposed to use this law. So I'm going to take a concrete example. The use of any law of physics is to be able to predict something about the future given something about the present. So all problems that we solve can be categorized that way. So I'm going to take a very simple problem, a problem to which I will return in great detail later on, but let me first start with this problem, which I will do very quickly now, and we'll come back and do it more slowly later, but at least it's a concrete problem. The problem looks like this. So here is a table, and here's a spring, and here's a mass M, here's a force constant A. I want to pull it by some amount, a force constant K. I want to pull it by some amount, capital A, and let it go. So that's the knowledge of the present. Question is, when I let it go, what's this guy going to do? That's a typical physics problem. It can get more and more complex. You can replace the mass by a planet. You can replace the spring by the sun, which is attracting the planet. You can put many planets. You can make it more and more complicated. But they all boil down to a similar situation. I know some information now, and I want to be able to say what will happen next. So here I pull the mass by an amount A, and I want to know what it will do next. Remember, when we go back to the laws of Newton only tell you this, and we've been talking about, is this useful information? First thing you have to know, in order to use the laws of Newton, you have to separately know the left-hand side. You have to know what force is going to act on a body. You cannot simply say, oh, I know the force on the body, it is M times A. MA is not a force acting on a body. A is the response to a force. You got to have some other means of finding the force, and in this case, the force on the mass is due to the spring. So I pull the spring by various amounts, and I see what force it exerts. Now I think you know now in practice how I know what force it exerts, right? I pull it by some amount, attach, say, the 1 kilogram standard mass. I see what acceleration it experiences, and M times that acceleration, or 1 times the acceleration, is the force the spring exerts. So I pull it by various amounts, and I study the spring, and I have learned by studying the spring that the force it exerts is some number K, called the force constant, times the amount by which I pull it. If I start off the mass in a position where the spring is neither expanded nor contracted, that's what we like to call x equal to 0. So I pulled it to x equal to A. Now what I'm told is, when you pull it to any point x, that's the force the spring exerts. So this is part of an independent study. People who work in spring physics will study springs, and they will find out from you find out and tell you when anytime you buy a spring from me, it'll exert this force. And they figured that out by pulling the spring and attaching it to various entities and seeing what acceleration it produces. There, the masses are taken to be known, because you can always borrow the mass from the Bureau of Standards, or we discussed last time how if you have an unknown mass, you can then compare it to this mass and find out what its value is. So every object's mass can be measured, and then the guys making the spring have studied what it does to different masses and figured this out. Now you come with this mass and you say, what happens when I connect it? Well, I'm assuming the mass of this guy can also be found by comparisons, the way I described to you last time. So we can always find the mass of any object. We went into some length. Then Newton's law says this is equal to ma, but I want to write a as the second derivative of x. So you now go from a physical law, which is really a postulate. There is no way to derive F equals ma. You cannot just think about it and get it. So whenever I do physics, I will sometimes tell you this is a law. That means don't even try to derive it. It just summarizes everything we know in terms of some new terms, but it cannot be deduced. On the other hand, the fate of this mass can now be deduced by applying Newton's law to this equation. Now this is a new equation. You may not have seen this equation before. For example, if I told you, forget the left-hand side, if I told you the right-hand side is 96, I think you guys know how to solve that, right? You have to find a function whose second derivative is 96 divided by m. You all know how to do that. It's t squared times a number, and you can fudge the number so it works. This is more complicated. The time derivative of this unknown function is not a given number, but the unknown function itself. In other words, x itself is a function of time. This is called a differential equation. A differential equation is an equation that tells you something about an unknown function in terms of its derivatives. You can have a differential equation involving the second derivative or the first derivative or the 14th derivative, whatever it is. You're supposed to find out what x of t is given this information. So one thing is you can go to the math department and say, hey, look, I got this equation, what's the solution? And they will tell you. Now, sometimes we have to do our own work, and we can solve this equation by guessing. In fact, the only way to solve a differential equation is by guessing the answer. There is no other way. You can make a lot of guesses, and every time it works, you keep a little table, then you publish it called Table of Integrals. So I have in my office a huge table. Mark Caprio's got his own integral. We don't leave home without our table of integrals. I got one at home. I got one at work. I may want to keep one in the car because you just don't know when you will need an integral. Okay? So people have tabulated them over hundreds of years. But how do they find them? They're going to find them in the way I'm going to describe to you now. You look at the equation and you guess the answer. Let's make our life simple by taking a case where the force constant is just 1. Okay, it takes 1 Newton per meter to stretch that spring. Let the mass of the object be 1 kilogram. This is just to keep the algebra simple. Later on, you can put any m and k, and we'll do all that. Then what am I saying? I'm saying, find me a function whose second derivative is minus that function. Now, as a word problem, maybe it rings a bell, right? Do you know such a function? Exponential is good. Another one, yes? Trigonometric functions are good. So I'm going to temporarily dismiss the exponential. I will tell you why. An exponential function is actually a very good guess. You can say x equals e to the t, for example. The trouble is this is growing exponentially. And we know this spring mass system, the x is not growing exponentially. Or you might say, well, let me fix that by making it minus t. Then it quickly comes to rest after a time and doesn't move. We sort of feel we want this thing to be jiggling around for a long time. So the exponential function is even better than this function because it says, take one derivative and I reproduce myself. But that's too much. We only want a function that reproduces itself. When you take 2 derivatives, and that's where the trigonometric functions come in. So I make a guess. X of t is cosine t. And you can check if you take 2 derivatives, it obeys the equation. The second derivative of x is minus x itself. But do I like this solution? Or is there something not fully satisfactory? Yes?
So wait, did you cancel out the negative when you...
Pardon me?
It says dx, d squared x over dt squared is x. Would it be negative x?
It will be negative x. Let's do that. So let's take dx dt is equal to minus sine t. Then take one more derivative, d2x over dt squared. Derivative of sine is cosine. So this is minus cosine t. But x was cosine t. So it's really minus of the x I started with. Yes? So you had a question or?
I was thinking you wrote it up there as x, right? I'm confused. And now
Oh, this one.
yeah.
Caught on film. Yes, that's a mistake. Okay? That should be minus. Very good. Look, it makes me immensely happy when you guys catch me. Of course, it becomes an addiction. You try to catch me sometimes. It doesn't work, but keep trying. This time, you're absolutely right. That's why you were looking confused. Anything else? Everyone follow the way this very elementary problem is solved. It's solved by making a guess. So you're right. So the minus sign was wrong, but now you agree everything is working. This is the answer. But no, I meant something else is not quite okay with this. Yes?
The function will also work if you added a factor of a sine also?
Yeah, that first of all, I can add some sine of t and it'll still work. But more importantly, if I put t equal to 0, I get x equal to 1. Why should it be true that I pulled it by exactly 1 meter? I could have pulled it by 2 or 3 or 9 meters. I want to be able to tell how much I pulled it by at t equal to 0. Suppose it was pulled to 5 meters and released. I want x of 0 to be 5. The point is, you can easily fix that by putting a 5 here. Does it screw up everything? It doesn't, because the 5 just comes along for the ride everywhere. And don't think it's 5x, because this 5 is part of x. So you can multiply your answer by any number you like, and you pick that number which reproduces your initial displacement. So if you pulled it by 5, you put a 5. So now we are very happy to describe this problem. It is true you can put sine t, but in this problem we don't need it. Here's an answer that does everything you want it to do. At the initial time, it gives you 5 times cosine 0, which is 5, and that's what you told me was the initial displacement. Initial velocity, if you take a dx dt, is proportional to sine t, and at t equal to 0, that vanishes. That's correct. You pulled it and you let it go. So the instant you released it, it had no velocity. And it satisfies Newton's laws, and that's your answer. I want to do this simple example in totality because this is the paradigm. This is the example after which everything else is modeled. Yes?
How do you know that it's not sine?
Pardon me?
How do you know that it's not sine t?
You mean at t equal to 0, if the answer was sine t, well, sine t vanishes at t equal to 0. And cosine t doesn't vanish, has a robust value of 1, but I want a value of 5, I put a 5 in front. Look, you guys may have a few more things to say about this problem because this is not the final and most general solution to the problem. It is a solution that certainly works for the one example I had, which is a mass being pulled to 5 meters and released. So carry this in your mind. This is really, to me, the most important thing I can tell you right now. The way F equals ma is applied in real life is half the world is working on the left-hand side, finding the forces that act on bodies under various conditions. In this example, the force is due to a spring, and by playing with the spring, you can study the force it exerts for various displacements or various amounts by which you pull it. And in this example, if you pull the spring by an amount x, it exerts the force minus kx, and you can measure k and you put the label on your product and you sell the spring with a given k. Other people are measuring masses of various objects, and they've decided the mass of this is whatever, maybe 1 kilogram. You put the two sides together and you find the response of the system for all future times. And what this tells you then, you can now plot this. This is a graph that looks like this. Goes from 5 to minus 5 and repeats itself, and it's very nice. That's what we think the spring would do. Now, you think this is a real spring or I'm missing something? Is this the whole story? Yes? is friction, because we know if you pull a real spring, it's not going to oscillate forever. It's going to slowly stop shaking and pretty much come to rest. That just means, who do you want to blame for this equation? Do we conclude now that something wrong with Newton's laws? Or what's the problem?
The K coefficient should not be.
Pardon me?
The K coefficient will.
The fault is not with the K. Yes?
We didn't take into account all the forces. Friction is another force.
That is correct. So we will say we have missed something. There's another force acting on this mass besides the spring. That's the force of friction that will oppose the motion of the mass. So you can say one of two things. Either you can say something is wrong with Newton's laws, or you can say we've not applied Newton's laws properly because we haven't identified all the forces. So if you never knew about friction, you do this and you find, hey, it doesn't work. The mass comes to rest, whereas the theory says it should oscillate forever. So you are at a fork. Either you can say Newton's laws are right, I'm missing some forces, I'm going to look around and find out what they are. Then you will derive friction from that. Or maybe it's time to give up Newton's laws. It turns out, even if there is no friction, this is not the correct law of physics. Correct law is given by Einstein's relativistic dynamics. This does not satisfy the relativistic dynamics. By that I mean, if you really pull a real mass by 5 meters or whatever and release it, its motion will not be exactly what I said, but it will be off by a very, very, very tiny amount that you probably will not discover in most laboratories. But if the mass begins to move at velocities comparable to that of light, then this equation will be wrong. So people say, oh, what kind of business are you in? Every once in a while somebody is wrong. I tell you right now, everything we know is wrong. You know, it's no secret. You can publish it, you can tell the whole world, this practitioner said everything is wrong. Well, it's wrong in this limited sense. Is Newton right or wrong? Well, Newton didn't try to describe things moving at speeds comparable to light. He dealt with what problem he could deal with at that time. So it's a law that has a limited domain of validity. You can always push the frontiers of observation till you come to a situation where the law doesn't work. But the special theory of relativity doesn't also work all the time. If the mass becomes very tiny, becomes of atomic dimension, then you need the laws of quantum mechanics. That's wrong too. So things work in a certain domain, and sometimes you abandon the formalism, but don't rush to do that. In this case, the problem is not with formalism, but due to friction. So you have to make sure you got all the forces. Once you got all the forces, it still doesn't work, then of course the experimentalists are very happy because there's something wrong with the theory, then you got to find the new theory till that works. Okay, so that's the cycle. So it's an ongoing process. Physics is still work in progress. This is work as of 300 years ago. And no one's found anything wrong with Newton's laws, provided you don't violate two conditions. You don't deal with objects moving at speeds comparable to that of light, and you don't deal with objects which are very, very tiny. The notion of what's very tiny will be very clear when you learn quantum mechanics next term. Right now, there is something rough called tiny. There's things like atomic dimensions. All right. So now we are going to do more concrete problems, but I wanted to write that up for you as a simple, solvable, worked out example that displays everything that happens in physics. All right. So by the way, people are always looking for new forces. You know, that electrical forces. You find a charge on a table, it's not connected to a spring. I bring another charge next to it and this guy starts moving. What do? A body accelerating without any force. I can say Newton is wrong, or I can say maybe there's a new force between that body and this body, and that will turn out to be the electrical force. Electrical force occurs whenever you take something, you know, you take a cat and you take a piece of amber or you rub it, you do various things, then you put them next to other things and they're attracted or repelled. Then you discover you're charging things, and that's how electricity was discovered. But you know, you don't have to have a cat. If you have a buffalo, you can take it with a buffalo, still works. Then you got to find out what you really need to find electric forces, but you find there is a new force, and you know you've got a whole new force to study. Then you got to find out what's the cause of the force. Turns out it's not the mass of the object. It's something else called electric charge. Then how does the force vary with distance? Well, it varies like 1 over r squared. You know that. So that's how you slowly study and identify new forces. So the forces were found in the order of gravitation first, and then electricity and magnetism, and now of course there are new forces called strong forces, there are weak forces, they all act in the subnuclear level. So that's why that business is not done. We are not finished with the left-hand side. We're still looking for new forces. Okay, so now I'm going to start doing problems in 2 dimensions. Everything I did last time was 1D. You know, you're pulling something, you're pushing something, you got one block connected to a second block, to a third block, and you pull it. We have done all that. So we're going to elevate this to higher dimensions. And as you know, in higher dimensions, acceleration is a vector. And so force better be a vector, because when you take a vector and multiply it by a number, you get something else. And there, by that process, you've gone to higher dimensions. So let's take, again, simple problems and try to make them more and more complex. And you cannot tell me eventually you agree the problem is complex enough. I will crank it up as we go along. At some point you'll plead for mercy, then we'll stop. But there is no limit to how difficult mechanics problems can be. If you go back and read Cambridge University exams in 1600 and 1700, they were really difficult problems. That's why we invented quantum mechanics, which is a lot easier than those problems from Newtonian mechanics. You can make it as hard as you like. So I'm just going to do a few, then once you got the idea, you stop. But again, we're going to start with easy one. Easy one is a table on which this mass is sitting doing absolutely nothing. And we want to study that guy and understand it in terms of Newton's laws. Because we are in 2 dimensions, you got to have 2 axes. So here is my x and here is my y. So the first rule is, if f equals ma, we are really saying I times fx plus j times fy is m I ax plus m j ay. It's a vector equation. The force has to be a combination of I and j, because nobody, by the way, I'm working in the xy plane. I told you I don't need to go to 3D for a long time. In 3D, every vector is some amount of I and some amount of j. That's true for f, that's true for a. You write it out. Then I told you if 2 vectors are equal, then the x components have to match, and the y parts also have to match. You can see that if I draw 2 arrows on the plane and I tell you this arrow is the same as that arrow, it's the same. It's got the same horizontal part and the same vertical part. So this is really 2 equations, and I'm going to apply them to this block. So when I look at this block in the x direction, it's not moving at all. There are no known forces acting in the x direction, and therefore it's a case of 0 equals 0. Did I miss something? You guys look a little worried. Yes? Okay, now I look in the y direction. If I look in the y direction, I take this block and I draw its free body diagram. Namely, I write all the forces on it. So that is the force of gravity, mg. By the way, this m is a big M or small m. Let's change the figure to small m so that the rest of the equations are right. The little mg is acting down. If that's all you had, the block would fall through the table. It's not doing that, so the table we know is exerting a force. The standard name for that is n, and n stands for normal. Normal is a mathematical term for perpendicular. You say this vector is normal to that vector, you mean they are perpendicular, and here we mean this force is perpendicular to the table. They are the forces in the y direction. In the y direction, n is a positive force, it's with a plus sign, mg is a negative force, and that's equal to m times ay. It's interesting that in this application of the Newtonian equation, I'm going to say that I know the right-hand side. I know the right-hand side is 0, because I know this block is neither sinking into the table nor flying off the table. It's sitting on the table, it has no velocity, it has no acceleration vertically. So that has to be 0 because I know the right-hand side. So Newton's laws, quite often either I will know the left or I will know the right. Either I will know the force or I will know the acceleration. So if this is 0, I come to the conclusion n equals mg. Okay, this is a very simple example, but this is how you figure out how the Newton's laws worked in this particular problem. Okay, now I'm ready to introduce another force, and that's the force of friction. As you all seem to be aware, there is generally a force of friction between this mass m and this table. So how do we learn there is a force of friction? Suppose someone said, how do you know there is friction? Here is the mass. What experiment will you do that tells you, hey, there is another force called friction? Can anybody tell me something you would do? Yes?
Maybe put the mass on an incline.
Okay, but suppose it's on this table, but you are around. You can do what you want. Yes? Go ahead.
Constant speed. In order to move it to constant speed, you have to apply force.
That's possible.
But
That's
when
good.
you move an object at constant speed, there's no force.
That's a very good answer. One answer is you find that to keep it moving at constant velocity, you have to apply a force. That means the force you're applying is canceled by somebody else because there is zero acceleration. That's got to be zero force. Yes?
Just apply force to it and push it on the table and it will stop eventually. And that tells you that there must be a force that's acting.
Very good. Or even before that, even before it starts moving, you find that if you push it, it doesn't move. Right? I try to push the podium. Well, I don't know my own strength, but I'm going to imagine I push it, it's not moving, but if I push hard enough, it will move. What's happening before it moves? I'm applying a force and I'm getting nothing in return for it. So I know there is another force opposing what I do, and that's called the force of static friction. The static friction is when the body is not moving. So I'm applying a force F. Let me give it some other name. Little f. No, that's not so bad. Little f is the name for friction. So I'm going to apply a force called F sub me. You can label these things any way you like. Okay? This particular notation is not caught on because people are not as interested in what I think as I am. But right now, I'm going to call it F sub me. I invite you to invent any notation you want because there's nothing sacred about notation. At least I want to convey to you that notion. So I call it F sub me. I'm applying to the right. Then I know that it's not moving. Therefore, there has to be another force that cancels it. But how much is the other force? Yes?
Equal to F sub me.
That's correct. So it is not a fixed force. Static friction is not a fixed force. It's whatever it takes to keep it from moving. It will not be less than what I apply because then it will move. It cannot be more than what I applied because then it will start moving backwards. So it will do what it takes to keep it from moving. So static friction is a force which has a range from 0 to some maximum. So let's call it the force of friction is less than or equal to some maximum. And that maximum turns out to be a number called the coefficient of static friction times the normal force. The force of friction seems to depend on how much normal force the table is exerting on the object, which in our example, if you want, in our example, not always, this is always true, but in our example, you may replace it by mu s times mg because n is equal to mg. So the force of friction seems to depend on how heavy the object is that's sitting on the table. But what does it not depend on that it could depend on? Can you think of something else? Could depend on but doesn't? Yes?
The amount of surface area.
Doesn't depend on the area of contact. In other words, if this was a rectangular block, it doesn't seem to matter whether it's doing that or whether it's doing that. You might think, hey, that's going to be more friction because there's more contact, but it doesn't. So it's interesting not only what it is, but what it's not. Okay, this is called the coefficient of static friction. So you guys should remember that the force that friction applies is equal to the force that I apply up to a maximum of this. And once I beat the maximum, it'll give up and it'll start moving. Once it starts moving, you're going to have a situation like this. I apply F sub me this way, and friction will apply a force which now is called mu sub kinetic times normal. So the force of friction is different when it's moving as compared to when it's not moving. It's slightly less once the body is in motion. So it's always true for all situations, mu sub kinetic is less than mu sub static. Okay? So this is how you characterize friction. You study various objects and you find out friction certainly depends on the nature of the two surfaces. Given that constant, it seems to depend only on the normal force and not on the area. Yes?
So is mu sub kinetic less than the maximum for mu sub?
Remember, mu sub kinetic is a fixed number,
Right.
maybe 0.2. Mu sub static is a fixed number, 0.25. If it's 0.25 for static, it means if the normal force is some mg, up to quarter of the weight is the frictional force it can apply to prevent its motion. Suppose I apply a force on a body which is originally 1/10 of its weight, it won't move. 2/10 of its weight, it won't move. Quarter of its weight, it's a tie. 0.26 its weight, it'll start moving. Once it starts moving, frictional force will be 0.2 times its weight, not 0.2, because the kinetic friction is less. This is just the summary of friction. Okay, so far even though I used vectors, most of the action is just in one or the other direction. Yes?
Is mu k also independent of the surface area?
No. It again seems, it can actually depend on many things. Friction is something we don't understand fully. But it depends only on the normal force, just the way I described it. Okay, now we are going to do the one problem that has sent more people away from physics than anything else. Do you know what it is? You haven't heard about the problem that sends people away? Okay, this is called the inclined plane. A lot of people may not remember where they were during the Kennedy assassination, but they say, I remember the day I saw the inclined plane. That's the day I said, I'm not going into physics. Because this is very bad publicity for our field. You know, you come into the subject hearing about relativity and quantum mechanics, and then, or maybe gravitation and astrophysics, and we hit you with this. So why am I doing this? Well, if you can do this and you find it boring, you can move on. But if you couldn't do this, you have no right to complain, because this is the entry ticket into the business. You've got to be able to do this. Only then I can tell you other things. Okay, so we'll do this quickly. I'm watching the clock. I won't linger over this, but we have to do this problem. Okay? So let's quickly finish this problem. So here's the problem. There is a mass, m, sitting on the inclined plane. It makes some angle here. You want to know what it's going to do. All right, we know it's going to slide down the hill, but you want to be more precise. And the purpose of Newton's laws is to quantify things for which you already have an intuition. So the only novel thing about the inclined plane is that for the first time, we are going to pick our x and y axes not along the usual directions, but along and perpendicular to the incline. That's going to be my x and that's going to be my y. And I ask, what are the forces on this mass? Well, I've told you, first deal with contact forces. The only thing in contact with the mass is the plane. The inclined plane can exert a force in general along its own surface and perpendicular to its own surface. But I'm going to take a case where there is no friction. If there is no friction, by definition, it cannot exert a force along its own length. So it can only exert a force in this direction, and we're going to call that N. Then there's only one other force. That's the force of gravity, which we agreed we have to remember. Even though the Earth is not touching this block, if the Earth is somewhere down here, it's able to reach out and pull this block down. So let me show you the forces. So here is N, and here is mg. These are your forces. And with no friction, that's it. That's the key to doing any problem I give you in any exam, no matter how stressful. I guarantee you'll get it from Newton's laws, provided you write every force that is there and don't write any force that is not there. So this is it. These are the two forces, and the mass will do what these forces tell it to do. So what we want to do then, since my axes are in this direction, I have to take this mg and write it as the sum of two vectors, one which is pointing in this direction and one which is pointing in that direction. So if I add these two arrows, I get mg. That's called resolving the force into some other direction. Now the key to all of this is to know that this angle here is the same as this angle here. In other words, if mg is acting down, that angle theta is the same as this angle theta here. This is going to be used all the time, so I'll tell you a little trick that tells you how I figured that out. Theta is the angle between the horizontal and the incline. Now you've got to agree that if I draw a perpendicular to the horizontal and I draw a perpendicular to the incline, the angle between those two perpendiculars will be the same as the angle between the two lines they began with, because perpendicular means rotate by 90. If you rotate both lines by 90, the angle between the rotated lines is the same. The vertical is perpendicular to this horizontal, and this is the perpendicular to the plane. Once you got that, the rest is very easy. So in the x direction, I'm going to write the following equation: mg times sine theta. So you got to understand that this part here will be mg times sine theta, and this part here will be mg times cosine theta. You got this, something you better get really used to. If a vector is like this and you want the force in that direction and the angle between is theta, then you put the cosine. The component that's adjacent to the vector is cosine, and this one here is the sine theta. So I got the horizontal part in the x direction. I got mg sine theta, and that's it. There's nothing else. That's got to be equal to m times ax. Remember, ax is not horizontal. Ax is along the incline, downhill. In the y direction, I write n minus mg cosine theta is m times ay. That's simply writing down Newton's laws as two laws, one along x and one along y, and putting in whatever we know. What happens next is up to what else we know. Well, we know that this block is sliding down the hill. It's not going into the block, nor is it flying out of the block. It's moving along the block. That's the reason we chose the coordinate to be perpendicular to the block, because that coordinate, the y coordinate, is not changing. Even though the block is sliding down the hill, when it's sliding down the hill, the usual x and y coordinates, if you define them this way, they're all changing. But by this clever choice, it's always at y equal to 0. So it has no y coordinate, it's no y velocity, it has no y acceleration. So we know this guy is 0. So this is an example where we know the acceleration by this kind of argument. From that we deduce that n has to be mg cosine theta. Okay, then you come to this fella here. There we found out that ax, you cancel the m, and you find is equal to g sine theta. So that's the big result. It'll slide down the hill with an acceleration g sine theta. This is a good way to measure g, by the way, because if you drop something, it falls too fast for you to time it. But if you let it go down an incline by making theta very small, so sine theta is very small and the gradient is very low, the body can accelerate with a much slower acceleration downhill, because it's reduced by this factor sine theta. Okay, here's another thing I should tell you right now. Most of us, when we become professionals, don't put in numbers till the very end. So if you're told the incline is angle of 37 degrees, g is 9.8, don't start putting numbers into the first equation. We don't do that, and I know for some of you it's pretty traumatic to work with symbols. And sometimes in exams they say, oh, you had all these problems with symbols. But I want to sell you another idea. It's much better to work with symbols than with numbers till the end. Why is that? First of all, if you put numbers in, and I suddenly tell you, hey, I was wrong about the slope, it's really 39 degrees and not 37, you're going to do the whole calculation again. But this way, you come to the formula and you say, what's your theta? You change your mind, okay, that's the new theta. You change the value of g, you made a better measurement, that's the answer. Then you can see if your problem had some mistakes in it. Suppose you got g squared sine theta. you will know it's wrong because this is an acceleration, that's an acceleration. The units have to match, and sine theta, of course, has no units. Then maybe you got your trigonometry wrong. Maybe it's really g cosine theta that should be the right answer. How do I know it's sine theta? You can do a test. We know, for example, as the incline becomes less and less inclined, you got to get less and less acceleration because it's going downhill less and less. And when theta goes to small values, ax also diminishes. Or if you take your incline and you really make it almost vertical, and in the end you make it completely vertical, the block is just falling under gravity. So when theta is 90, a becomes g. So you can test your results. So be prepared for that part if you are in this course. I will give you some homework problems in which numbers are not put until the very end, or I may not even ask you to put the numbers in. Because the thing is to get this formula, because anyone can take the numbers and put them in the calculator. So that's going to be part of our agreement that we will work with symbols. And if you look at any calculation we do, if you caught me in my office, I'm not putting numbers in very early. I mean, I cannot wait to find out what the answer is, but I keep the symbols till the end, then I put the numbers. Then you can vary different numbers. You can say, what if the gravity was weaker? I go up to Denver and do the experiment. Will I get a different answer? You will. So how things depend on the input parameters is interesting. Here's another interesting result. What is missing in this formula that could have been there? Pardon me? The mass. It doesn't seem to matter what the object is. That's an interesting property of the result, right? And that's because m canceled out of the two sides of that equation. So these are all interesting features you would not know if you kept numbers everywhere and you get a equal to 0.62 meters per second squared. To me, that number doesn't tell me as much. In the end, I want to know the number, but the formula is very interesting. All right, so now we're going to make it a little more complicated. We are going to now add friction to this. So here is the block, but now there's a coefficient of friction, and let's say the block is, let's ask the following simple question. I think it was related to what one of you guys said. Let the block be at rest, and theta is an angle I can vary. Maybe there's a little thingy here, you can turn it back and forth. Let me crank up theta and see when it will start slipping. In other words, there is a coefficient of static friction between the block and the plane, and I want to know, like parking your car, in San Francisco, what angle can it take before it starts sliding down? So let's write the forces, and let's write F equals ma. So the forces are again here. Let me cut to the chase and write mg cosine theta here, and here, mg sine theta here. What shall I write for friction? Do not write mu s times n, because the frictional force is anything you need up to mu s times n. In other words, if theta is very small and mg sine theta is very small, the frictional force will be in fact mg sine theta. It will equal whatever it takes to keep it from slipping. But if I've cranked up the angle to that maximum angle beyond which it cannot stay there, let's give a name to that angle, that is sine theta star. Well, at the maximum angle, friction is doing the maximum thing it can do. Then we can certainly say mg sine theta is then equal to the static friction times n, which is now mu s times mg cosine theta. Again, the mass cancels. So it doesn't matter what kind of car you parked on the slope. It only depends on the following. G cancels too. So whether you park your car on the earth or park it on another planet, this is going to be the same restriction, which is that tan theta has to be less than or equal to mu s. Equal to mu s is the critical value. Less than that is acceptable. Okay, that's a simple problem. If you tilt it to more than that, it'll topple over. So now let's take another problem where the block has started moving. It's going down the hill. Now what formula do I write? You notice that I'm not writing every step every time. Each time I deal with it, I'm going to do some things faster. For example, I already resolved gravity into two parts without going through the whole song and dance, because you know how to do that. Now I put in the friction. So now I got mu sub kinetic not equal to 0, mass is moving. You can ask, what's the acceleration now? So the horizontal equation along x is going to be mg sine theta minus mu kinetic times the normal force. But allow me to write for the normal force mg cosine theta, and that's got to be equal to m times ax. Now, can you do this? That's the test. This is not enough to watch me do this and say, okay, he seems to know what he's doing. The question is, can you do this? Would you have thought about this? Do you agree that I'm not doing anything beyond Newton's laws when I do this? Yes, each one of you should ask. If you cannot do that, you have to deal with that now, because this is only going to get compounded. On the other hand, if you can do this, you know everything I know about Newton's laws. This is all there is to Newton's laws and how to apply them. So you cancel the m. So notice here, this is the normal force, but I've taken the y equation that says normal force is mg cosine theta, put that here. Then I find acceleration is g times sine theta minus mu sub kinetic cosine theta. Okay, here is the result. Ax is what I'm calling A now. I want to study this in various limits. First limit I take is no coefficient of kinetic friction. I get back to my sine theta. Well, let me try the following interesting limit. I crank up the coefficient of kinetic friction more and more and more. Look what happens here. Sine theta and cosine theta are fixed numbers. If this becomes larger than some amount, than say tan theta, what happens to this expression? A is negative. Now what does that mean? Block is moving uphill. Now do you buy that? So what's wrong? I mean, I took the equation, right? I told you all the time how you can study various limits. Something is wrong. It says if kinetic friction is very large, the block will move uphill.
K can't be greater than 1.
That's not the reason. Yes? Oh.
Can't be greater than the static friction.
No, that's not the reason. I mean, you can also vary the angles, maybe keeping k at some value. Vary the angle so that this number times that can beat this. Then what happens? Yes?
You already assigned the direction of mg sine theta downhill.
That is the point. Okay. Let me repeat his answer. That's the correct answer. You're right about kinetic being less than static and so on. But you can always imagine keeping that number constant, but changing the angle so the cosine gets bigger and sine gets smaller. At some point, you agree, cosine will beat the sine, because sine is going towards 0 and cosine is going towards 1. But the correct answer is, in writing this force law, I'm assuming the force of friction points to the left, uphill. That is correct only if the body is moving downhill. But if you got an answer where A was negative, therefore you're going uphill, the starting premise is wrong. So one very useful lesson to learn here is, when you apply a formula, don't forget the conditions under which you derived it. And don't apply the result to a case where the answer does not belong to the domain that you assumed you're applying it to. So the trouble with friction is the following. Friction is not a definite force with a definite magnitude or direction. At least magnitude is definite, but direction is not definite. It is uphill if you're going downhill. It's downhill if you're going uphill. Okay, it's like the constant opposition to motion. Whereas force of gravity, the normal force, everything else is a fixed direction. You can draw it once and for all. So in a formula where the forces are what they are in any context, you can apply the formula in any limit. But if the frictional force assumed a downward motion, don't apply it when the block is going up. Okay, so I'm going to do one more of these inclined planes and then pretty much done with the inclined plane. Okay, this is the problem of two masses. There's a rope that goes over the pulley. Let's call this little m. Let's call that big M. And this angle again is theta. And no friction. You can mix and match various things, but let's keep friction out because I'm trying to do something different here. So we want to know what these guys will do now. So first guess is, well, capital M looks so impressive compared to small m, so maybe it'll go downhill. You got to realize that's, of course, fallacy, because capital M is a symbol, the value associated with maybe 1/10 that for small m. But if big M really is bigger than small m, then am I sure it'll go downhill?
The mass has to be greater.
Pardon me?
The mass has to be greater, not necessarily the volume.
No, I'm saying if the big mass M is bigger than the small mass m, is that enough to say it'll go downhill? Yes.
Because it depends on the angle.
Depends on the angle, because part of the mass is not helpful in going downhill. See, if I had a pulley like this, then you're absolutely right. Big guy wins. Now it's not clear, because this has got all of gravity pulling it down. This has got only part of gravity pulling it down. So let's skip this direction. It's not very interesting. Let's look at this direction, for which the equation is the following. If I just took that block, it's got mg sine theta acting down, and this rope will exert a certain tension T here, which I don't know. Under the combined effect of these two, I can say mg sine theta is equal to, minus T is equal to ma, where A is assumed to be positive going downhill. That's one equation. Then I come to this fellow here. This block, well, it's got little mg acting down and tension acting up. I'm sorry, guys, I made one mistake here. I think you know what it is. These should be capital M. That should be capital M, sorry for that, and capital M. For small m, the equation is T minus mg. Now, let's be careful with what I do next. I'm going to say it's little m times A, which is the same A. You should all understand why the acceleration in magnitude is the same. We're not saying the direction is the same. This is accelerating downhill at some angle. That's accelerating uphill. These are not equations which are vectors. These stand for equations along certain directions. This is the up-down direction here, and that is up the slope, down the slope direction for that one. But I think you realize if the rope is inelastic, if this mass moves down 1 inch, that's got to go up 1 inch. Therefore, if it goes 1 inch in 1 second, so will the other guy. They will have the same velocity and they will have the same acceleration. So that's why there's only one unknown acceleration, A. Once you realize that, you're done. Because now we know what to do. Whenever you see a minus t and a plus t, you add them, and you get g times m sine theta minus little m. On this side is going to be big M plus small m times A. Can you see that? So let me short circuit one step and divide by big M plus small m. So that's the formula here. And again, you got to ask, does it make sense? Now you notice that for it to be positive, namely to go downhill, it's not enough if big M is bigger than small m. Big M sine theta should be bigger than small m. That's because m sine theta is the part that's really pulling downhill. M cosine theta is trying to ram it into the inclined plane, and that's being countered by the normal force. Second thing to notice is, can I use this formula when small m is bigger than big M sine theta? In other words, can I use this formula when A becomes negative? After all, I did all my thinking saying it's going down, but can I use it when it's going up? Yes. And the reason, anybody want to say why that's okay here? Yes?
No friction.
Pardon me?
No friction.
Right.
The friction is a force which is dependent on which.
That's correct. All the forces I drew here, they're not going to change their mind when you change the body's motion. Gravity is always going to pull down. So all these forces are fixed in magnitude and direction, and therefore once you got a formula for positive A, you can apply to negative A. But you cannot do it when you have friction, because in friction you assume the direction of motion. All right, so now I'm going to leave the plane. This is it. We are finished with the plane. You are not finished because, don't clap here, because I got a homework problem by popular demand. 2 masses, 1 pulley, and friction. That's to really say we're finished with the plane. Once you can do that, You've graduated from this boot camp. You can handle anything else. But that's not something I want to do in class. That's something you do in the privacy of your room. Put all these things in and crank it up. And you'll also have enough time. But that's got some interesting angles you should think about. Okay, so now I'm going to do physics that basically involves rotational motion. But let me do one Mickey Mouse problem and let it go because I assigned it to you. Typical problem is there is a tree here, there's a tree here, and there are two ropes, and there's some backpack hanging here with some weight. You are told what that angle is, and you're told what that angle is. You're supposed to find the tension on these two ropes. I think it's fairly simple, so I won't do the details, but you know what you're supposed to do. You take these two tensions, break them into horizontal parts with sines and cosines, and into vertical parts. Horizontal parts better to cancel because this backpack is not going anywhere horizontally. The vertical parts of these two, which will be in fact additive, should cancel the weight of the object. That gives you two simultaneous equations for T1 and T2, and you can fiddle with them and solve them. Well, by the way, I should tell you, if you got some equation like T1 sine theta 1 equals T2 sine theta 2, or that minus T2 sine theta is 0, and another equation involving T1 with some numbers and T2, somehow you seem to have trouble the other day when there were sine thetas here, whereas if these had been numbers like 3 and 4, you knew how to solve these simultaneous equations. But I want you to realize that the solving of the simultaneous equations for T1 and T2 involve forming combinations of these coefficients to eliminate either T1 or T2. So when you add them, one of them drops out. And that doesn't depend on whether these are trigonometric functions or any other numbers. You eliminate it in the same way. Likewise, on the right-hand side, instead of some numbers like 3 and 4, you have the weight W of this mass. Well, if you multiply this equation by 3, multiply everything by 3 and juggle them. So you should get used to eliminating coefficients which are not simply numbers, which are symbols, sines, cosines, but you know how to, if you had a sine here and a cosine there, for example, how will you combine them? Maybe you will multiply this by a cosine and that by a sine, and if you subtract, it will drop out. You got to do stuff like that. Okay, but it's important in a level, physics 200 level course, you'll be able to solve those things. Okay, now I'm coming to the interesting problems in which motion involves going in a circle. So here's one problem. This is a string on which there is a mass, and the mass is going around in a circle. This is like in amusement parks where they have these dangling little tiny baby rockets, and you sit there and it starts spinning, and instead of being vertical, it starts lifting up. You want to know why it's lifting up. So if this angle here is theta, and this is some mass m, and is going around in a circle with velocity v, and the radius of the circle is, say, r, we want to find some relation between this angle theta and these other parameters in the problem. So what do? I apply F equals ma. That's it. And I'm going to get everything by applying F equals ma to this guy. So here's that mass. The tension on the rope can only be along the rope. Rope is not a rigid object. It cannot exert a force perpendicular to itself. It can only pull it along its direction. That's the tension on the rope. That is mg. And that's it. Under these things, it's going to obey F equals ma. So what I do with this tension is I trade this guy for two forces. This is T. If that angle is theta, let me see. That angle is theta. So this is T sine theta, and this is T cosine theta. So you trade that oblique T for two T's not in the actual simple directions. The fact that it's not going up or down vertically tells me mg is equal to T sine theta. I'm sorry, yes. Okay, then in the other direction, T sine theta is the horizontal force. That's got to be mass times the acceleration. At the instant where I've shown the object, because it's going in a circle, it has an acceleration. in this direction with size v square over r. Therefore, if you divide this equation by that equation, you will get v square over rg equals tan theta. That's the angle that string will assume. So if you knew the velocity, you can do this problem. Okay. Then here's another interesting problem. When you go on these roads, if you're going in a circle, suppose this is your car, I'm looking at you from the top, you're going in a circle. Anything wrong? Going in a circle, you're accelerating towards the center, someone's got to provide the force. That's what Newton says. That force is the friction between your tire and the road. In fact, it's a case of static friction. You might think it's kinetic because the car is moving, but it's not moving in this direction. So it's a static friction that keeps you from slipping. So you need a certain static friction so that N times mu static, where N is equal to mg, must be equal to mv squared over r. If you didn't have the static friction, your car will not be able to make the curve. It will fly off. So what people have done is to find a clever way in which you don't have to have any friction, you can still make the turn. That is to bank your road. So imagine now you're going into the blackboard and you're turning left, and the road looks like this going away from me. Now I don't have to draw this thing. This road is a track, a race track, going round and round like this. And I gave it some angle theta. This road has no friction, so it can only exert a force that way. But let me resolve that force into two parts, one like this and one like this. Again, if these two have an angle theta, that is the same angle theta there. And that is the mass of the car this way. So what do I find? I find n cosine theta equal to mg, and n sine theta equals mv squared over r. Therefore, if you again take the ratios, you will find tan theta equals v squared over rg. I think this may be a little fast now, but you guys can do the algebra. What that means is the following. If you want a car to go around a bend at a certain speed, 40 miles per hour or so many kilometers per hour, and the road itself is part of a circle of radius r, it doesn't have to be a full circle. At that instant, it has to be a part of a circle. Then if you bank your road at that angle, you don't need any friction to make the turn. You got to understand how we beat the system. If your road, instead of being flat, is tilted, then even though the road can only exert a frictionless normal force, now part of the normal force is pointing toward the center. In fact, this picture is not drawn to scale. If you drew it that way, this part of the vector is horizontal and directed towards the center of the circle on which you're orbiting. That's how you do the banking. In any good system of roads, you'll find there is banking. Okay, I'm going to do the last problem because it's in the homework, and maybe I'm a little late today. I apologize for that. The last problem is very famous, very important. That's the loop problem. As you know, the loop is when you come down on a track, you go on a circle, and for a while you're upside down. And the famous question is, why don't you fall down? What's the trick? Does it violate Newton's laws? And so on. We'll find we can understand it fully with Newton's laws. But we'll find out that in order for this thing to pull it off, its speed at that instant has to have a minimum value. And the application of Newton's law to this object is very simple. Here is gravity. What about the track on which it's going? What's the direction of the force the track exerts? Pardon me? Down? Anybody said up? A track cannot exert a force upwards. Down. So everybody, track, mg, are all acting down. So you see, that's when you get a little worried. Because this guy's up there, all the forces are down. So we got to ask, so what does that mean? Well, I have to agree they're all down. I say T plus mg is the downward force. That's got to be mv squared over r. Therefore, T is equal to m times g minus v square over r minus g. So what does that mean? If this t comes out negative, you're dead. Because if it's negative, you want the track to exert an upward force, and it cannot. In a real amusement park, they have other t brackets and so on to support you. But if you really believe in the laws of physics, you don't need any of that. You just got to make sure this number is positive. For it to be positive, you need v squared bigger than or equal to rg. So you got to make sure when you're on the top, you have this minimum velocity. If you go faster than that, that is just fine. If you go faster than that, t will be some positive number. So here is the interesting thing. Have we escaped the pull of gravity? How come we are not falling down? And the track is not helping us. It's also pushing us down. Yes?
The velocity vector is moving towards the left, and the force, the total force is changing the direction of the velocity towards the center, but it's still going along a circular path.
Okay.
Even if that's the force radial to it.
Yes. So the point is, if you have an apple with two forces both pushing down, that apple is accelerating down. And accelerating down means really falling towards the ground, towards the center of the circle here. In this example, it is definitely accelerating. But that acceleration is not added to zero velocity, in which case it will pick up more and more speed. It's added to a huge horizontal velocity. So in a tiny time, you give it a little velocity like this, your new velocity points at a new angle. That just means your body has come here and is stopped going like that and started going like this. Therefore, downward acceleration does not mean coming closer to the ground. It only means your velocity vector is changing its direction. On the other hand, if you have no velocity vector, downward accelerations mean what you think it is. That is why if you drop an apple from here, it has an acceleration due to mg. If the track was pushing it down even more, it will fall towards the ground and hit the ground. But here, it actually has an acceleration, but doesn't mean you're any closer to the center. Going around in a circle is an example of constantly accelerating toward the center, but not getting any closer. That's the way vectors work, and you should think about that.